platform. And of course, it raises the question about funding and collaboration that I think already was touched upon in the last few summaries. And the session actually ended with a call for a NORLab catalog egg day session over Zoom. So I'm just passing along the call. Okay, so now in the third breakout room, we started the conversation about follow-up. I think it's a question that is very important in this era of big data because we will have a lot of big discovery and the need for follow-up will be clearly bigger than the resources that we have. And the question was, first, what do you follow? So you have two types of follow-up, either follow-up of a sample or follow-up of a rare gem that is isolated. And in case of a sample, most often than not, you can actually determine the number of objects that you need to confirm your science question. So those are some things, some statistics that needs to be into your proposal. But in case of a rare gem, it's more of a high risk, high reward thing, right? And so in those cases, you can't actually predict the number of targets that you need. So there is really different way you can go at it, and it's hard to share the time between both of those. People, I think, at the end said that in this era of big data, we'll have a big homogeneous survey. And so it will lead to a lot of population discovery that are discovered the same way, and so in a uniform way. And so maybe we should get away from trying to understand precisely one object, but more think about population. Yes, and then it was clear that there will be problems and oversubscription with spectroscopic follow-up for different science case, because a lot of them actually require a big precision. So for example, 10-meter class telescope. But it was said that there's also cases where you can find cheaper alternative. And so people talked about a narrowband photometry to obtain metallicity, for example. It was also brought up that we should not forget that some follow-up needs timing and other don't. So we can be flexible in function of that too. And finally, it also raised a question of equity because most of the people that would be able to access those follow-up will be people in institutes that have proprietary access to those big telescopes. And so it raised the question of how can we make those follow-ups not depending on in which institute you are. And so I think there was a big push for more collaboration also, which resonates again in all of those summaries. The last question that we tackled was kind of a summary question. It was about what people got out of this conference, what are they most interesting about in this big data era, and what are the big challenges that they see. And I think that machine learning was one of the big highlights, the fact that it is a tool that we can use to really harness all the data that we will have to do amazing discoveries. But a lot of people actually said they didn't feel prepared to use machine learning. So it's really a call to have learning capacities or to hire more versed people in machine learning and to bring along different communities, for example, the industry community, in order to be able to merge observation people, for example, with machine learning people and create great things. And it was said that this conference was a great example because it really raises those questions and merge different type of people. Then a challenge was raised with how can we combine all those big data survey together, for example, LSST with Euclid or LSST with Roman, and discussion are ongoing, so it's a good news. And finally, I think a question was raised about the computing capacity, because all of that, machine learning, big data sets, will require a big computing capacity, and it's once again raised the question of equity. The institutes will we have access first to those type of computing are the same that have a lot of follow-up power, for example. And so there may be a way to create a public computing power place But once again, it's a difficult question, I think, hard to answer. And we finished all the session by a reminder that it's great to be an astronomer in those big data era. Thank you.
Thank you very much. Great summary. And I hear echoes of some of the same points made in other breakouts. Yeah. Yeah.
Hi, yeah. So there was a point about basically ML education. And it kind of goes a little deeper than that. There are a lot of places, a lot of universities where coding is not a required course for astronomy. I'm currently teaching basically Python for undergrads as an undergrad at UC Berkeley. And the Astro department, it's basically a 60-person class with about 5 of us teaching, and we aren't getting paid. And as we've raised this so many times, and the big problem that the department has come up with is that they don't have enough faculty to teach the course. And that's a funding issue, but also a priorities issue. And kind of falls back on like, do we need to grab some software engineers who've been, I was talking about this a lot yesterday. Do we need to grab some software engineers and integrate them into our pipeline process and keep things up to date so that we don't need to do software engineering as astronomers? But yeah, was there any discussion about how to address the priorities and funding?
So I think there were more questions than answers, because obviously this is a funding problem and it's very hard to solve. So I think what you said echoed in our discussion, but there were no clear answer because it's clearly very deep and complicated things to solve. So I'm sorry, I don't have a solution for you.
Yeah, Eric.
Well, maybe that's kind of similar. That's exactly kind of what Link is trying to. But you see, that's like a philanthropic effort, right? So it's money from the sky, and it has its challenges as well. Surprising challenges. It's not as simple as one would think. I'm sorry.
No, I mean, so on this, I mean, machine learning is another tool, and historically the community isn't particularly great at teaching anyone how to use tools because we prioritize physics, which I understand, right? And it's not just finances, it's also time. There's 120 credit hours to graduation, and you need to, if you're going to add requirements to students who have to spend longer at college, et cetera, you need to remove something. So it's like, who needs to know about stars? You know, we'll just teach them how to write software. No, we're not going to do that. So I think the challenge is that we need to help foster literacy in the tools that we use, but that we cannot, as a community, I think, encourage everyone to become specialists in every damn tool. Right? So there is a call for collaboration. There's a call for literacy, but I do think that we also have to not go overboard and, we're going to spend all our time teaching people how to do X, Y, Z, because there are other tools and other techniques that we need to also have literacy on to be a professional astronomer.
On the following note, how many papers are like 15 pages on how we establish a neural network and how we clean data and all that, and like 3 pages or 1 page about actual physical outcomes of our analysis? I mean, the duplication of effort is huge. Cleaning the data often can be done in the same way for a number of scientific analysis. But how do we do it? We clean the data, we publish a paper, we publish a code in some repository which is completely unreadable, and then 10 people who follow this paper, they will reproduce this code from scratch, introducing new errors. It's not just that we don't have enough people. It's mostly that we do not do it effectively. So it's primarily, once again, it is such like a question of sociology and mindset and how we do this work, not just like we lack resources. Resources are enough. We are training more astronomers than we can actually give job to. How many people are just forced out? But it's a question of how we do it.
Yeah, good points. Asli?
Yeah, so I have like ideas for everyone. So the first thing I would say is I think a lot of this like data sharing, what code you publish is what's rewarded in the field, and what's rewarded in the field right now is paper output, not beautiful code output. So I think that when you say like that's a sociological issue, that's something like we need to internally change within the field. If that's something that we want to promote, it needs to be rewarded. In terms of, you know, how do we add ML to like an already full curriculum? I think that we need to think about software skills the way we think about math. And if we're going to have a math methods class, maybe there should be a software methods class. If we think that we can incorporate that into the curriculum, I think that there's a lot of room to say teach stellar astrophysics using something like MESA, or, you know, incorporate this into the way that we teach our existing courses. And then finally, I think that there is also room for thinking about, you know, high impact workshops like the carpentries or something, where you get a foundation of coding, maybe in a 2-day workshop that people can set aside 2 days in the summer or something for, that gives a baseline skill that you can then build on from there.
Good points. I think Dave had his hand up.
Yeah, I've been listening to this discussion goes now and for the last couple of days, and this is actually not new in the sense of if you talk to people who build instruments or telescopes or data systems or image processing software, all things which have occurred for, 100 years, every one of those communities has had a similar discussion. And so, it does come, Eric, I think, captured the discussion for astronomers, the dilemma pretty well. It's like, do you want people to be astrophysicists first, or do you want them to be technologists first? And this goes on for a long time. No instrumentationalist in this country has ever felt as appreciated as he or she wants to be. And you're absolutely right. People get rewarded for writing paper. And I guess I'll make the side comment that you talk about the reward within astronomy, you should really be thinking about the reward structure within your university, because the people who are sitting on your tenure committees are not just the people in your departments, college and your provost office and your president's office. And it's often the groups outside of your department that can, I'll say, quote unquote, save you from your colleagues. And I'm saying that from the perspective of someone who both came up through the system and was a dean for 5 years. So, what's the solution? Well, the solution is that at least for instrumentation and for image processing software, eventually there were groups in North America and in Europe and in East Asia who actually specialized in these things, and they became the providers. So, we know who the instrument groups are. Not every university has an instrument group. We know who wrote the image processing software, which eventually became that one in the marketplace that was IRAF in the day. Now it's going to be something else. It may be that there needs to be a similar effort around, machine learning. And, and I would say, if for any of you who are at an Aura institution, here's the shameless plug, you ought to be pushing for Aura and the NSF to be supporting the National Observatory and the affiliated things in the Rubin sphere to actually make sure that it's being funded to provide that level of expertise so that the rest of y'all can get on with doing the astrophysics that you want to do.
Wonderful points all around. An additional thing is that there's a lack of consistency, right? So up down to the like classes and teaching yourself Python and stuff. Like when I did my undergrad, I did it at the University of Washington. We had astronomy coding as part of the curriculum that was integrated. That's wonderful for me because now I can use that information and I have those resources. And then every single undergrad that works for me now, I funnel them those Jupyter notebooks, and I funnel them that knowledge and the textbooks, and I can do that and spread that information in my corner. But that's not enough, right? And it really is an additional layer of there needs to be some level of flexibility, because again, not everybody needs to be doing the same thing. Not everyone needs to or should be specializing in the same area. But if everyone is so different in the way that they teach and the content and everything, then it's just, it's an Ouroboros. It's a never ending circle. We're never getting anywhere.
So yeah, I agree, I think most closely with you. This isn't a problem of specializing in ML. It's an equity barrier for students who have never touched a computer before. I teach GitHub, command line, basic Python, and that takes the whole semester. And a 2-day workshop isn't really enough. And then students who didn't come from schools that had a course in coding, let alone Python. AP Comp Sci is Java, very different. It requires a whole lot of reorientation. That's how I learned Python, was after Java. And so you change the people who are coming into this field. If you do not have an undergrad or even like entry grad level course in Python, if you don't know Python, you don't get research and you don't get into grad school. That is the reality of the environment that I'm coming up in, which just is not okay, especially since there's a huge correlation between who has coding education and who has money.
Those are great points. I mean, I think the literacy of what you need to be a successful researcher today is very different from what it was 20 years ago. So, and we do need to recognize that. I wonder, if anything, this is going to change when, the current generation becomes faculty. They will. That's yeah. How about Guillermo, and then let's move on to the next one. Or
Okay. So I agree with most of the points here. I think Charlie was doing a very good point. I had also similar experience of teaching at an intro to Python class, but at graduate level, when most of the students were supposed to have coding experience, and you realize that they still need to go not into repeating recipes, but understanding what a computer is doing. It's a way of thinking. And I think there is a barrier there, and there is a resistance I've seen because I agree the curriculum is limited. You have a limited amount of time and classes that you can teach on programs. So I think the approach that we were, or with some colleagues, what we could favor was maybe you need to start with an introductory class to computing and coding at a very low level, early, as soon as you can. You cannot do it on first year because, with nonlinear algebra, some things are really hard to understand, I think. But then basically try to do all of these coding activities on each class, and it's part of the whole program. Basically, each professor should be teaching how you solve problems on your daily work.
Yeah.
Because at the same time, something that you don't recognize when you're saying, we had some resistance from other colleagues saying you need to teach astrophysics because you're basically doing astrophysics. But the problem is that you have to recognize that not everyone will continue working in astrophysics. So what alternate options, which are valid options at the end, that's a very good discussion. What tools you give to graduates or undergrads to look for other options that is not the usual academic path. And that's also really important to consider. You are not forming only astrophysicists. You have to think you are forming a person who needs to survive after they graduate.
Yeah. Those are excellent points. Okay, let's thank the Milky Way group and Aaron.
Okay. Can you hear me? Yeah, so I'm presenting on behalf of the Exoplanet and Moving Object working group or breakout group, I guess you would call it. I felt some peer pressure to have a word cloud, so I made a word cloud of our Google Doc of notes. It looks oddly sparse, but we did talk for the full 1.5 hours times 3 days. I think it's just free software. You get what you pay for on the word cloud. Anyway, I thought it might be good to clarify a little bit what the scope of this breakout group was to begin with, since in some ways it's all connected, but in some ways there's a few different elements mashed together. So the scope that we considered was exoplanets, solar system, i.e. like asteroids and so forth, brown dwarfs, and proper motions in the Milky Way. Mm. Did I need to keep the Zoom thing fully open? Was that the key? No, that was not it. Which browser is this? Is it in Chrome? Where is it? Yeah. Yeah, I think I had clicked on something other than Chrome while I was standing up here, so it's probably my fault. Anyway, most of the structure, this is just going to be a few takeaways, but I did want to mention what we talked about on each day roughly. So on the first day, we discussed the landscape of the sort of current or upcoming major surveys or data sources that we're really interested in for this type of science. The second day, we had more of an emphasis on tools that were relevant for finding these types of rare gems in these data sets. And these tools that we discussed included things like brokers, archives, science platforms, machine learning, and citizen science. And then day three, we just had kind of like a forward-looking discussion about what we thought were the most exciting types of rare gems that we might find in this area of science over the coming years. So yeah, one of the first themes or takeaways that came up within our group was that generally we felt our science was best served if we would be able to effectively work across different surveys, different data sets, ideally without sort of the worst case scenario of every researcher reinventing their own cross-matching method or cross-matching tables for, you know, say Rubin and Roman or Rubin and Euclid, what have you. And we thought that science platforms were quite relevant here. Examples of current ones being NORLab Astro Data Lab and Rubin Science Platform. It still remained a little bit unclear to us whether there will really be in the end like a central place to analyze all these big upcoming astronomical data sets in the near future. I know there are aspirations and hopes of doing that, and that would be great if it pans out. The other thing that came up was that cross-matching is a little bit more difficult for moving objects than for some other classes of objects that stay static, like galaxies. And so, you know, having a cone search functionality maybe doesn't always cover you for especially solar system objects or maybe even faster moving proper motion objects. The second takeaway was that within our group, we had a lot of interest expressed in brokers and what could be done with them for moving objects, both solar system and Milky Way, even though our impression has been that for the most part, brokers tend to be engineered for the case of like a static transient that's staying in the same position but changing in flux. Although we did note some existing examples of functionality that are already in place for solar system objects or for, yeah, mainly for solar system objects. So one is the Think broker, which I believe is is built primarily for the upcoming LSST data. And then there's also this NeoFixer one that I show below a screenshot of. The third of four takeaways has to do with kind of like the themes of machine learning and citizen science and how they connect to one another. So within our group, we felt that there's a lot of good evidence to show that machine learning and citizen science both have worked really well for projects related to finding moving objects. Examples of these that came up were the Daily Minor Planet, which is kind of innovative and on the Zooniverse in the sense that they're putting out new data every night, or most every night whenever there's new data available, which is kind of cool instead of only having a release every 6 months or year. Another one that came up was Backyard World's Cool Neighbors, which is an example that combines machine learning and citizen science. We discussed how we felt that the machine learning plus citizen science synergy could be sort of furthered by closing the loop, so to speak, and actually taking the classifications from the volunteers online and feeding them back into the machine learning algorithm, this new trading data, to try to iteratively do these improvements. So Cool Neighbors, for example, we haven't got to that stage yet, but it would be interesting to really see that iteration more in progress and take advantage of the human labeled data sets. The last point here is more of a question than anything, but it wasn't entirely clear to us whether or not citizen science as we currently do it will scale to data sets like LSST. Maybe there's a ton of enthusiasm in the public and it will scale naturally, or maybe there's some like barrier that we really hit where it just stops being effective. There's too much data. So I think that'll be interesting to see, but we didn't have an answer for that. And then the last takeaway slide here is just kind of a list of what were the most interesting things that we could come up with as far as rare gems in this area of exoplanet, solar system moving object. So trans-Neptunian objects, centaurs, Earth Trojans, interstellar objects like Oumuamua, moons of solar system planets, but really, really tiny ones. DCAM has been very good with this, so I assume LSST will be as well. We didn't actually discuss this much, but I felt it was obligatory to put in here Earth-like planets around M dwarfs. Essentially, that would certainly be quite a rare gem. Very low temperature brown dwarfs at the temperature of Jupiter, never been found before. Very nearby systems neighboring the sun, which could exist but may not, and hypervelocity stars. So these were the areas that we thought would be ripe for rare gems type of searches and discoveries. So thank you.